So let's actually compute some partial derivatives here. We're going to use the limit definitions to compute the partial derivative of this function at the point 2, 3 in the x direction and in the y direction. So again, folks, the interpretation for this is if you go to the point 2, 3 on your function here, and this is not going to be an accurate graph of the function, but here is the point 2, 3 on the graph. So in fact, there's, let's see, 1, 2, 1, 2, 3, here's x, here's y, there's that point. And that's actually the ordered pair. If you were to plug that in, that would be the ordered triplet, 2, 3, 12. But the question we ask is, if you leave y alone and you let x vary, the graph of that function is the partial derivative of f with respect to x at the point. And so we could ask the question, if you put a tangent line right there, what is the slope of that tangent line? And that's what we're going to compute. So let's go ahead and do so. Partial f, partial x, evaluated at, let me write it this way, evaluated at 2, 3 is equal to the limit as h approaches 0. And here we're just going back to those definitions from the previous page. So that's going to be f of 3 plus h, f of 2 plus h, 3, minus f of 2, 3, all divided by h. Well, that's equal to the limit as h approaches 0 of 2 plus h quantity squared times 3 minus 2 squared times 3 all over h. So I'm doing the pointwise definition here. And now the limit techniques, because this is a limit in one variable, are similar to all of the techniques you used in Calc 1. So remember, our goal is to eventually try to cancel out a factor of h. If we did some foiling here, what we'd have is 4 plus 4h plus h squared, all times 3 minus 12 over h. And continuing, we get the limit as h approaches 0 of 12 plus 12h plus 3h squared minus 12 all over h, which is the limit as h approaches 0. And we do some more canceling. We can eventually write this as h times 12 plus 3h all over h. And here comes that step where we're able to cancel out the factors of h, which were preventing us from doing direct substitution. And we're left with the limit as h approaches 0 of 12 plus 3h. And if we evaluate that via direct substitution, that is just 12 plus 3 times 0, which is equal to 12. Meaning, if we go to the point 2, 3 on this function, and we proceed moving parallel to the x-axis from that point, we're going to have a tangent line there with a slope of 12. So let's do the same thing for the other point. So let's compute partial f, other point, I meant the other direction, partial f, partial y, at the point 2, 3. So that's equal to the limit as h approaches 0 of f of, careful, 2, now we add the plus h to the y coordinate, because we're taking the partial derivative with respect to y, minus f of 2, 3, all over h. And continuing, we get the limit as h approaches 0. So let's see here. Plugging that into the function, we'd have 2 squared times 3 plus h minus 2 squared times 3 all over h. And if you clean this up, notice this would give us 12 plus 4h minus 12 all over h. And I'm just going to jump to it, folks. Hopefully you see that that limit comes out to be 4. So the partial derivative of this function in the y direction at that point is equal to 4. Meaning if you go to the point 2, 3 on this function and you move in the y direction, my picture's not accurate, if you move in the positive y direction, the slope of your tangent line is a positive 4. Okay, folks, so we're going to get a lot more practice with that. This is just an introduction. You're going to have to do some problems with the limit definition just like you did in calculus. But quickly we see that a lot of our one variable rules carry over. So if I ask you to compute the partial derivative of this function here with respect to x, the way we could treat this is we could say, hey, we're going to fix whatever the y coordinate is when we compute that. That means we can treat the y variable as a constant as far as changing x is concerned. So when I go to take this derivative, I'm simply going to treat y as if it were any old constant and take the derivative with respect to x. And so we'll justify these steps in class, but look, this is how we compute the partial derivative with respect to x. It would be 3x squared, and then I'm going to put plus 0 because this is just a constant term as far as x is concerned, and so the derivative of a constant is 0. Then I'm going to take the derivative of this, and the derivative of this would be 8xy cubed, where the y cubed is just treated as a constant, just as the 4 is, and it comes along for the ride, and we took the derivative there. So we could clean that up as 3x squared plus 8xy cubed. There's the partial derivative of this function with respect to x. The partial derivative of the function with respect to y says take this function f of xy, and we're going to, at any point, we're going to fix the x coordinate and then let y vary. Because the x coordinate is fixed, that means we treat the x coordinate as if it were a constant. So what would the partial derivative of this with respect to y be? Go ahead and pause the video and work through that, and I'll put up the answer in a moment. Give it a shot. So when I did so, this is how it simplified. That's what I ended up with. Folks, we've got a lot more to do with partial derivatives. This is just our introduction, but hopefully you see that in a lot of cases, computing them will be just simply relying on our Calc 1 understanding of how to compute derivatives as far as the computation goes. But it's exceptionally important that we realize that these partial derivatives are not at all the same as just computing the slope of the tangent line. Returning to our very original example here, it did not make sense to ask the question, if you move away from that point, what are you increasing or decreasing? The notion of a tangent line in general does not apply to a multivariate function. It only applies when you say proceed in a certain direction. Now is the function increasing or decreasing? And the two directions we choose to start off with are our partial derivatives, where we fix either x and let y vary, which would be this case here, where we fix x and let y vary, or where we fix y and let x vary, and then compute a slope of a tangent line on that individual trace. Folks, I hope this is a good clarification. We'll discuss this more in class. Thanks for your patience.